This diagram shows several one-way streets in a downtown. The figures in red are flow rates of the cars moving through the intersections in cars per hour. The variables x, y, z, and w represent unknown flow rates of cars traveling in those directions indicated. We are asked to write a system of equations that will keep the traffic moving. Well, to keep the traffic moving, it means on every hour the same number of cars needs to come into an intersection as is going out. If fewer cars are going out, we have a traffic jam. So we want to keep that the same. We're asked to then write that in row reduced echelon form. We'll use our graphing calculators to help out with that. And then finally, we're asked to solve the system provided that z, for some reason, either because of a lighting system or construction, is limited to 50 cars per hour. Well, the primary idea here is that in each intersection, the number of cars in has to equal the number of cars out. So let's just look at intersection 1 to start with. If I combine the two directions, in 1 hour, 380 cars will be coming into the intersection. In that 1 hour, z plus w cars will leave the intersection, and we need those to equal to keep traffic moving. All right, so I'm gonna write 4 equations based on the 4 intersections, and I'm gonna write them right now in the format of in equals out. And that way they're all organized the same. Eventually, we'll rewrite them the way we typically look at a system of equations. So the second intersection, cars going in, well, that's x plus w. Cars going out, well, I have 200 and 400 make 600. In the third intersection, cars coming in, I have 200 plus y. Cars going out, I have x plus 30. Intersection 4, cars going in, 70 plus z. Cars going out, y plus 20. Well, if I'm going to get this in row reduced echelon form, it means I need to write this down the way we would traditionally write down a system of equations. So I'm thinking about writing them down in the way I'd have a spot for an x term, a y term, a z term, a w term, and then equals some constant, right? So I'm going to rearrange these equations. Well, this first equation says z plus w is equal to 380. So now I've written that one in my system of equations in that way I'm imagining. So 0x plus 0y plus z plus w equals 380. All right, in intersection 2, I have z plus w, so, x plus w, so I have x plus w equals 600. In intersection 3, I need to rearrange things. I want to keep x positive, so I'm going to imagine taking y away from both sides and taking 30 away from both sides. So in that way, I'd have x minus y. X minus y is equal to 170. 200 minus 30. I'm going to do the same thing here. I'm going to take z away from both sides. So I have y minus z is equal to, and then 70 minus 20 is 50. And so there is my system of equations that governs this system of intersections, with our goal being to keep the traffic moving. I'm going to write that system on the next board so that we can work with it and answer the rest of the questions. All right, so now we're asked to write this in row reduced echelon form. So I'm going to enter this into my graphing calculator. So I grab my graphing calculator, I hit second matrix, and I'm going to choose to edit matrix A. I have 1, 2, 3, 4 equations, which means I'll need 5 columns. This will be a 4 by 5. Entering in this, I see 0, 0, 1, 1, 380. So 0, 0, 1, 1, 380. And I just need to do that, pressing enter after everything I type in. And then the final row, I have 0, 1, minus 1, 0. Apparently I hit a button wrong there, so let's go back in there. I should probably just start over, but I'm not going to. So I had 0, 0, 1, 1, 380. In the second row, 1, 0, 0, 1, 600. Everything looks good so far. And now here, 1 minus 1, 0, 0, 170. All right, enter. 0, 1, minus 1, 0, finally 50. Okay, so I have my matrix entered in. I usually go back and proofread, but I'm gonna, since I kind of had to redo some of it anyway, I feel pretty good about it. Second matrix, math, go down to RREF, row reduced echelon form, and I was working in matrix A. And so let me write down this augmented matrix, because it's not what we actually wanted. It's not in row reduced echelon form. Down here I have a row of all zeros. Okay, well, this is as close to row reduced echelon form as we can get this matrix. And it turns out when you get a row of all zeros here, this is the case where I have a dependent system. This system has infinitely many solutions, because that last row is literally saying 0 equals 0. That's one of those true statements. Well, this actually makes sense. It might not be what we wanted as students, but if traffic's going to move through this intersection, I probably do really want more than one possibility that will work. Okay, well, we did our best, and then finally we're asked to solve the system if z equals 50. Okay, so z equals 50 cars per hour. So here I have an equation that says z plus w equals 380. Well, if I know z, then I know w. 50 plus w equals 380. W would have to be 330 cars per hour. All right, well, I found half the variables. If I can just keep finding things, I'm fine. And I can use anything that's written here, but I can also use information that's in my original matrix. And since I know z, and this says y minus z equals 50, I can find y. Y is 100, because when I plug in 50, I add 50 to both sides, I get y equals 100. And then finally, I just need to find x. Here I see x plus w equals 600. So x plus 330 equals 600. So I take 330 away from both sides, and x is equal to, I think that's 270. If z is 50, then this is my solution. And I know if I change z, I would get other solutions, because I was literally told that this had infinitely many solutions.